Hi guys, it's your guy Olumide, and today we'll be solving another one of the most commonly asked tech interview question. It's the design a tree DSA problem. It is tree related, trie related. Design a trie. So it's a DSA problem that's solved using the Trie data structure. So it's a problem that is commonly asked by top tech companies including Google, Amazon, Netflix, Meta, Apple, Microsoft, and other top tech companies. Okay, the problem statement states that design and implement a Trie data structure that supports the following operations. The first operation is to insert. So whenever I want to insert a word into the trie, and the return of the insert is none. Why? Because it's just inserting. So it's actually not returning anything, just insert. So it's inserting a word into the trie. And then another operation we want our trie data structure to support is the search, whereby we pass in a word that we want to search if it exists in the trie. So it's gonna be a boolean return true or false whether the word exists in the trie. So it's gonna return true if a word exists in the trie and false if not. We also have another functionality we want to add to our trie data structure. It is the as prefix. So it's also gonna return a boolean type, and what it does is that it returns true if the trie contains a word with the given prefix. So and false if not. So as prefix just have to do with, okay, go try check if at all there's that word in this tree. It doesn't necessarily need to be a complete word. Just try to check if that word is the start of any word or any branch in the tree. So it's a prefix. It's trying to check if the tree have something like that word as a prefix. Okay, considering some examples now, we have this example whereby we create a data structure and then we are calling the insert method of the data structure, and we are calling it on top, top. So we are trying to insert the word top into the data structure, and the next thing we do again is that we insert the word by bye into the data structure. And what we do now is that we want to try to check if the data structure have prefix to. Fine, it do have, even though it's actually a word called top that we inserted, but because there's actually a word that has the prefix to, so as prefix is gonna return true. And then we do a search of to. A search of to is actually gonna return false. Why? Because we actually do not have a word that is to in the data structure. Instead we have a word that is top. So, and then we now perform another one, insert to, where we actually inserted the to, and when we perform a search call again to the data structure, because we have inserted the word to, we can now return true for search to. So, and that's what we have right here. So you see that true is first returned for the as prefix because to exists as a prefix, but false is returned for the first call to search and the first call to the search method for the word to, because it's actually not there. We actually have the word top, not to. So, and then when we perform another search again to for to in the data structure, because we have inserted it right here, it returns true. So, and that's what we have. That's the explanation we have here, whereby we insert, and then we try to check the prefix and perform some search and insert and search. Okay, let's consider some constraint that is given to us concerning this problem. The first one is that the word and prefix consist of only lowercase English letters, so A to Z, right? So we don't need to worry about wildcard, about dots, about symbols, about other characters. So just English letter. And then the second constraint is that the length of each word and prefix is at least one character. So we don't need to worry about empty word and empty prefix. So whenever we perform a search, we definitely are going to be performing on at least a single character. So in solving this problem, is to design a tree class, right? So, and a tree class, we actually a tree, or is to design a tree structure, right? And a trie is definitely going to have tri node. It's actually consisting of nodes that are connected by edges, whereby each node represents the strings, or each character in the string that we are inserting into the trie, right? So we need a tri node. So first of all, what we do is that we define our tri node class to represent each node in the trie. And don't forget the properties we explained in our previous video in the introduction to trie. We'll be having the children. So each trie node should have a children attribute, right, which represents the branches, the children that branch out of that particular node. And then we have the is word attributes that will represent if that particular node is the end of a word. So if that particular node signifies the end of a word. So after doing that, we'll be doing that in the code. It's actually simple. You're gonna see it in the code implementation. Then to initialize the trie, we need we define the root trie node in the constructor. So don't forget, well, in the previous video that I did, I tried to show a trie structure. So whereby a trie structure will always have a root. This is it here. So we are gonna define this root in the trie node constructor. So in the trie node constructor, we're gonna define the roots. So because this root will be general to every other word or every other branches. Why? Because they're gonna all branch out from this root. So all of them will share similar roots, and we're gonna define it. So all words inserted into the trie will branch out from this root node, right? Okay, now let's talk about inserting a word into the trie. That is the insert method to insert a word into the trie. So the insert method is going to build the trie word by word, and what we mean is that a call to the insert method, now we are going to pass in a word into it, just like this, where you consider inserting the word byte into the trie. So that way, now by calling the method insert and passing in the word to it, is going to build that word into the trie. And then when we subsequently call more word, that's how you keep on building the trie. And one good thing about this is that the trie is going to avoid redundancy, meaning that probably one are passing bytes and one are passing bytes and one are passing, just little difference with the same prefix. Instead of having to create it multiple branches in the trie, it's gonna take advantages of shared prefix to use the same set of node. So let's consider inserting the word bytes into this particular tree now. So we first check if B, which is the first letter of the word that we're trying to insert into the byte, we first check if it is a child of the root node by querying the children of this root trie node. Don't forget that each trie node will have children attributes, which is actually a hash map, so, or a data structure that will contain each string and their node. So if that particular string is in the hash map, definitely we don't have to be redundant in creating a new tree node when we already have one that they can share together. So doing that, now we're gonna check, and because by checking into the children of this root node, we see that B exists. Don't forget, it will be the value B, just a string B will be the key in the trie in the hash map, while the node is going to be the value, right? So when we try to check if the first if the first character in the string is part of the children of the root node, we're gonna see that yes, it is. So, and definitely all we wanna do is that we just shift our current node from root node to this new node B. Why? Because we are not going to be creating a new node. We already have a word in the trie that have the same prefix B as the one we're trying to add. So we just want to navigate into B now to try to check if it even have another one like Y. So after doing that, again we are going to navigate to the next element in the string. So don't forget, we are currently at the node B, and now the next element and the next character in the string is Y. So what we want to do is that, okay, this is it here. When we're trying to perform the insert, we try to check if B is a child of the current node, which is the root node. So because it is, we are going to change our node, that is our current node, to node or children of B, so that it will reference this new node B here. Okay, doing that now, we are now at this current B. So we're gonna check again at this node that okay, does y a child of the current node? Fine. Y is a child of this current node B now. So what we're gonna do is that we're gonna set our node again to node the children of y. So what we do, what that means is that B is the current node B is the current node now. So we're gonna tap into its children. Don't forget, each tree node we have a children data structure, so that we keep track of the children. And visually we can say that the children or the child of B is y. So we are gonna reference it just like how we reference a value in the dictionary by saying node.children. So where children is a dictionary, then we are going to perform this selection to get the value of this particular key y. So we're going to set it to our node, so that could be our current node, right? So that means that we are navigating into this node now because it correlates with with y. So navigating again into this place, we move our character to the our pointer to the right. So from B now to T, to try to check if this current node y, if it has the node T. So fine, T is not a child of y only have a child E, right? So what we're gonna do is that we're gonna create a new child for y, right? Not entirely new. Don't forget that the children is a children, so y already have E in the as a key in the children hash map, right? In the children hash map. So we're just going to be adding T to it now because it does not exist. So what we're gonna do is that we're gonna create a new tree node. This is just simply how we do it, a new tree node now. And we're gonna assign the key T to it, so that will be the tree node for T. And what we're going to do is that we're gonna add it to the children of the current node y. So that will be node.children, so which is node y.children. Now we are now trying to create a new key value pair to represent T. So simply that's what we do. And after doing that, we are going to navigate into this new node T now. Why? Because we are trying to insert in the word BYTE. So we already gone through BY and we have created T, so we have to move into T so that it could have a child E, which is the last element in the last character in this string. So that's what we are doing here, that node equals to node.children of T. So that particular node that we just created for the key T, we are gonna set our current node to it. So doing that now, we are now here. So this place now is supposed to be right here, you understand, because it's the current node now. So now trying to check into the node T, that is just a newly created node actually. So it actually does not have any key value pair in the children hash map. So we are just gonna check anyways if E is not a child of the current node or not. If it is not, then we want to create a new tree node to represent to be the value for the key E in the node.children. That I mean, because this current node does not have a child E. So in the children hash map, what we're gonna do is that we're gonna create a new trie node, so that will represent the child E. So we're gonna create it. We're gonna add it into the children of our current node T. So and that what we did here. They said that node.children of E. So we are trying to add this key value pair into T, and after doing that, we now take that key value pair, which is node.children of E, I mean the value. So we now set our current node to that node, right? So automatically now E is our current node, because we say node equals to node.children of E, where node of children of E is actually this newly created tree node. Okay, doing that now, our node is now at this last our current node now is at this last E, and now that's everything that we can iterate through in the array, right? So what we just want to do is I want to set is what attribute to true. I mean, for this particular node, this is the last node, this is the last element and the last string in the word we are trying to insert into the trie. So we have to set this node.isWord equals to true, meaning that the isWord attribute is set to true to represent that okay, we have come to the completion of this word. Alright, let's talk about another method that we need. Don't forget, in the problem statement it was given to us that we should define some method, the insert, which we just speak about now, and then we have the search method as well. So this search method now, what we just want to do is that it's very similar to the insert as well. So because why it's similar is because just like insert, we are trying to insert a word, right? So similarly we are trying to search a word, so we are going to be navigating through the word one by one as we are searching for it. So if a node corresponding to the character in the word is not found at any point, we return false, because this would indicate that the word does not exist in the tree. So what we're trying to say in essence is that imagine we are searching for byt. Okay, sorry, let's say we are searching for be. Let's say we are searching for be, right? Be. So now fine, we are gonna navigate through through the string character by character, right? So first of all, we're gonna check if b is actually a key in the root node. So fine, it is. So we're gonna navigate into we're gonna set our current node to be b, and then we're gonna navigate to the next character in the string, which is e, to search if e is a child of b. So if you see, say that b is not a child of b, e is not a child of b, b only have one child, which is the child y, you understand? So because of that, there's no way we are gonna find be in this tree node, so we just want to return false. That's what this place is trying to say. And then here it's trying to tell us that okay, once you can successfully traverse all character in the search term, so consider be now, let's say that probably be is there, so we traverse b, we find it, then we find e as a child of b, definitely we'll be able to traverse every character in the search term. So then we return true only if the final word attribute is true. So the final nodes is word attribute must be true, so meaning that after eventually navigating through and retreating through each character in the search term and try to check if it actually occur in that order in the tree node, after doing that you now have to take the last node and try to check if its word attribute is true, because that is what we guarantee that okay, this is a word here, this is where the word completed. Don't forget we explained that the other time when we are trying to insert the word, the place where the word ends, we are going to set is word attribute to true. So let's just consider this now whereby we are trying to search for to. Look at this now. So from the root now, we see that we navigate into t, and then when we set our current node to node t, and we now try to check into node t that does it have a child 0 a child o. It do have. So after that we then try to check if his word attribute is true. So we are just gonna return node dot is word, meaning that the last node, which is the last current node, which is o, we're gonna try to check if his word is true. So if it is true, definitely it exists. If it is not true, no, it does not exist. It is actually just a prefix to a more larger word. Probably the word is actually toward. Imagine now, so you are not trying to search for to. Fine, to exists, but this is not a word in the tree, so it is toward. So and because of that we might return false for that, because his word is not true. Now searching for prefix for a prefix is very similar to what we just talked about now. Very similar to that, just that we are gonna just return true once we could navigate through each character in the string. We don't need to confirm if the his word is true or not. Imagine now, fine, the word we are inserted into the root into this tree node is byte and bye, right? We inserted bye and byte and cop, but now I want to check if the tree has a prefix of by. So we are not necessarily interested in whether that is a o word, or whether y, which is the last character in this word that we are trying to find the prefix, whether it has its word equals to true. We just want to check if b and y are if those sequence of node is in the tree. So and once we get it, we don't need to validate by checking if his word is true, we just return true. So this is how to solve this problem. We're gonna be going to the code implementation now. Kindly follow along. Let's go into the code implementation for design a tree problem. So first of all, we'll be defining the tree node, which is trie node, so which represents the nodes, each node in our trie data structure, right? We're gonna be so in the initialization for this class trie node that represents each node in our trie data structure, in the initialization we'll be passing in well, we don't have to pass in anything. So yeah, we don't have to pass in anything. So but we'll be defining the children attribute, right? So each children, so each node will have a children attribute, whereby it represents the children or set of sequence of node that branches out from that particular node, right? So imagine the case of interface and internet. So you see that at the node R, so that's where net branches out and face branches out. So that's what children will represent. So also they will have the is word attribute, right? So to represent if it is a word or not. So it's gonna be set to false. That is if it is the end of a word. So it's gonna be set to false by default, right? So that's it about the class for trie node. So now let's define the trie data structure itself. So this trie data structure itself will have the init, of course. So this is actually data structure that will be having the insert method, the search method, as prefix method, and the structure we want to design. So do we have to send in anything? No, let's just move on. So we're gonna be first of all defining the roots. So during the initialization, so the roots which will just be a trie node, right? So and what this actually means is that so for this particular trie structure, it's going to have a root whereby every branch will come out from, will come out from, right? So that's what this is just meaning. So let's proceed to define the insert method. So the insert method is gonna take in a word, right, that we want to insert, which is a string. So and then the return will be none. Why? Because we are actually just inserting into the trie. We are not returning anything. So and what we want to do is that first of all, let's define our and initiate our node. So we are gonna be setting our node to node.roots. Don't forget we've defined the initialization node.root to be a trie node that actually will not represent any character, just there for the roots, to represent the root. So now for character in word, right? So we want to iterate through each character in the word. So I want to check that, okay, if it is not, since we are trying to insert, if it is not in node.children, mean that if this character is not in node.children, so what we don't forget that our node is initially at the roots. So if it is not a children or a child of the root node, then we want to add it as a child of the root node. So we say that node is equals to node.children of this particular character is equals to trie node. So we're gonna be adding it into as a child. So and after doing that, we say that we set our node equals to node.children of C, right? So this way now we are able to set our node, because the node never existed in that particular current node, which is initially the root node. We are first of all going to create a branch for that particular word. So we are gonna set the node. So don't forget how we create a branch is how we create a branch is by adding that particular key value pair of the character and its corresponding node, which is like this, the character and corresponding node. So we add it to the child of the current node. So and that way now we can, if we say that node.children of C is gonna go reference that particular the node for that particular character. So we're not setting that node as the current node now, because any other node that we'll be creating now as we iterate through the word will fall under this new node. So something like this. So and that's simply what we want to do. So after doing this, we're gonna go on to the next character in the string. We're gonna try to check if it is not a children of the current node. We are gonna create a new node and assign it into the children of the current node, so that this particular current character could be a child of the current node. So what we're gonna do is that we're gonna shift our nodes to that particular new node that we created, that is the new character. So and then we'll just keep on building it like that. So, and at the end of the day, we have our last node, right? So we want to reference the very last node and set is word to true, so as to indicate that this is the that this last node is the end of the word. So that's all. So now let's define our search method. Our search method is gonna take in a word as well that I want to search for. So it's going to be a string now, so it's gonna return a boolean whether true or false, right? So and what we now do is that fine, we want to initiate our node starting from the root node to perform the search from there. So after doing that, we want to iterate through each word, right? So and then we want to check if not node.children of from that particular character. That is, if at any point imagine at the root node now, and the very first character, I mean the very first character in the word is not a child, definitely it never existed in the tree. If at the root node the very first character we're trying to search for does not even branch from the root node, is not a child of the root node, or subsequently it is not a child, then that word is not really in the try. So I want to return false. So otherwise it is, that is node.children of C exist, I mean okay, sorry, if not C in node.children. So this one, what I'm trying to say here is that if this particular character is not in the is not a child, is not part of the children of the current node, then there's a problem. Otherwise we wanna set our current node to node.children, that is, it is there of C, right? We're gonna get that particular, we're gonna reference the value of that particular character in the children of that current node, then we get the node and we set our current node to that particular node. So, and after that, now after doing that over and over again till we get to the very last character in the word, we want to return node, that is the last node that represents the word dot is word. So that way it's gonna return true if the node dot is word is true, that is, if that node is the end of the word, it's gonna return false if not, right? So simply like that. Def as prefix now is what we're gonna create next. Def as prefix, so it's gonna take in a word as well. So word, which is a string, is also gonna return a boolean, right? So okay, so similar thing is going to be done, just that the only difference is that we're not gonna return node dot is what we're just gonna return true straight. So if it could iterate through the whole word, the whole character in the word without returning false, that is, for each of these words is finding that character as a child in the current node, definitely we're just gonna return for and true. We are not interested in checking if it is the end of the word or not. So that's simply the difference. So we're gonna be setting this to self.root, right? And after doing that, oh sorry, let's do this. So and after doing that, we want to iterate through each character in the word that we're trying to search as a prefix. So I'm doing that here now. Okay, if not C in node.children, then we want to return false. If at any point you couldn't find any of the character as a children in the current node, then return false. So otherwise just set the nodes to the appropriate children. So node.children of C. So and after doing that, you can just return true. If you can loop through all the character without returning false, then return true. I'm not interested in whether it's the end of the word, we just want to check if it's the prefix. So I'm doing that now. That's actually, we've defined the whole method we need, the tree method. So and what we just want to do now is define the tree and create an instance of the tree. Automatically, in the initialization, the roots will be created. So and then we can now easily call the methods on the tree that we created. So we try to insert top, we try to insert by, so we now have the tree now have top and by. So now we now try to check if we try to print out if it has a prefix of to, we should print true. We are gonna see it down here if it's gonna print. I'm trying to run it now. So also we're gonna perform a search. You see that this search should return, oh, it returns an error, right? Let's see what could cause this in the insert method. So if not node.children, sorry, it's supposed to be if not c in node.children, right? So we're trying to check if that character is not in the node's children. So not if not node.children. Okay, so you see that first of all it returns a true, then it returns a false, and then a true. So you will see it now. So the first true will represent this one. So look at it here, true, then which represents tree.as prefix of to. Fine, yes, it has, because we have inserted the word top, so that have a prefix of to. So the other one return false, so which actually represents tree.to. Fine, we have a in the tree we have a prefix to, but we don't have a word to. We actually have a word top, so that's why it returns false. So similarly, the last one returns true, which actually is the a print to search for to after we eventually inserted to, so it's gonna return true definitely. So this is how to solve this problem, and I really hope you understand this. I really hope you understand this. If you do, alright, if you do, subscribe to my YouTube channel, please. Thank you.